striking this area and recondensing, right? And at equilibrium, the rate of departure is equal to the rate of capture. If the average amount of force that one of these species is held into the solution with is not a function of the local environment created by the solvent or solute, if the forces essentially between the solvent and the solute are the same as the forces between solute and solute and solvent and solvent, then the energy that those species are bound to the solution with is constant. And therefore, the rate at which these species depart and go into the gas phase is a function mostly of the surface area occupied by the molecules. So the more molecules there are on the surface area, the more opportunity they have for departure, right? If you change this, and if you say that, say we have pure solute, or pure solvent, if you say that the forces that the solute is held into the solution with under the pure conditions are different than the forces holding it into the pure solution, or sorry, in the mixture. If you say that the pure solute experiences different forces than it experiences in the mixture, then it'll have a different tendency to escape into the gas phase, and so forth with the pure solvent. So if the forces that the solvent experiences here are different than the forces that it experiences here, then it'll have a different tendency to escape into the gas phase. And you won't have a relationship where the pressure in the gas phase is simply a function of the mole fraction times the pressure of the pure. But in the case that those interactions are identical, you will have that simple relationship because the surface area available to the species is proportional to the mole fraction, and the forces binding the species to the solution are identical. So Raoult's law says that for ideal solutions, and we're now defining ideal solutions to be solutions where the solute-solvent interactions are the same as the solute-solute interactions and the solvent-solvent interactions. For those ideal species, this Raoult's law thing holds. Does that make sense? It's scary, painfully quiet out there. Okay. In that case, if you were to graph the pressure versus the mole fraction of a component, what you would have is that, say, XA is the mole fraction of the solvent. In a pure solute solution, the pressure exerted by the solute would simply be equal to its P naught, pressure when it's not a solution, right? The pressure exerted by the pure. As you start to increase the mole fraction of A, phase, whatever it is, the solute, as you begin to place that other species in, it starts to occupy some surface area, and so it exerts a pressure that's a function of the interactions that it feels, right? As you move the mole fraction, effectively dumping more and more of species A in the solution until it is approximately occupying all of the surface area available to it at the top of the container, then the pressure will be equal to the pressure of the pure. Yeah? This is not the way that most species behave. Like we said, for species that have similar interactions, this behavior can be expected, something like benzene and methylbenzene. So what's benzene and methylbenzene? There's benzene. There's methylbenzene. You look at these two molecules, and they're roughly the same size, and so each molecule occupies about the same volume at the top of that surface. And they're both kind of dominated by van der Waals interactions. And so the forces between these guys are roughly equivalent. Solvent forces are equal to solute-solvent forces. And so that chemical system obeys this relationship. A lot of chemical systems don't. And when they don't, you'll see that this is total pressure across here. The pressures change as you end up changing the mole fraction. Okay, they're both things that look like this. Instead of a linear relationship, there ends up being a curve when you look at pressure with respect to mole fraction. In the event that we have a situation where something is behaving ideally, then the pressure is related to the mole fraction as Raoult's law predicts. And that allows us to cast the Gibbs free energy of the species in terms simply of the P naught of the pure, the pressure exerted by the pure species, and the mole fraction of the thing in solution. So here is that derivation. We have that at equilibrium, the chemical potential of the gas phase, which we know is the mu naught plus RT line P for whatever the observed pressure is equal to the chemical potential of the liquid phase. And we said that for something that's behaving ideally, that the pressure that's observed is going to be equal to the pressure of the pure times the mole fraction. And so we can recast this equation, and we can say that the chemical potential of the species in the liquid phase is equal to mu naught of the gas plus RT times the natural log of the mole fraction times the pressure of the pure substance. So this equation gives us, based on Raoult's law, the chemical potential of the species in solution. We can simplify it by breaking apart that logarithm. Natural log of mole fraction times PA is equal to RT natural log PA plus RT natural log XA, where XA is the mole fraction. And here we're looking at a term for the standard chemical potential at 1 atmosphere plus a correction for whatever the actual pressure is, right? And we can kind of group this into one term that is the chemical potential of the species not in solution at the observed pressure, at the pressure that we're at. We call that mu A star. So this is the standard chemical potential of the pure solution at whatever our pressure is, that's some pressure other than 1 atmosphere, other than standard pressure, plus RT times the natural log of XA. Does that look familiar, that equation? Looks like that equation that we had for the gases, right? The chemical potentials of the gases. So if I take this equation and I decide to run a calculation like we did for the gas, the one we showed on the last page, I didn't write this one out, but you can imagine that if we say we're calculating delta G for this thing going into solution, delta G is G final minus G initial, and the G initial is going to be that mu naught term, and the G final is going to be this term that is a function of the mole fraction. If we run that calculation for delta G, we will get a form that is very similar. Hold on, I'm going to do this. Very similar to the one that we looked at for the delta G of the gases. So don't pay attention to this. I was beginning to solve a problem, and then I decided to stop solving it and just write the result because I didn't have time to write out the whole thing. But basically, for these ideal solutions, the solutions that obey Raoult's law, we have that the delta G of mixing for an ideal gas is equal to nRT times mole fraction times the natural log of the mole fraction, and you sum that thing for all of the components, and it looks just like the form that we had for delta G of the mixing of the gases. So real quick, I forgot to mention this on the last equation, but since the equations are similar, we'll talk about it again. What's the sign of this whole term? What's the natural log of something that's less than 1? Is it positive or negative? Right. And so since we're dealing with mole fractions here, we have terms that are less than 1. So all of this is negative. This whole thing is negative, and we said it was equal to negative T delta S. So basically, when we have an ideal gas or an ideal solution, the entropy change results in a negative contribution to delta G, right? And that's why for ideal systems, ideal gases, ideal solutions, the mixing ends up being a spontaneous process because entropy adds a negative component to that delta G. So for all of these ideal systems, we find that the delta G of mixing ends up being negative. In the case that you have a real solution, there's always going to be that negative term to the delta G from the increase in entropy, but there'll be some delta H term that might be negative or might be positive. And depending on the relative magnitudes of delta H and T delta S, the entropy term, you might have a mixing that proceeds spontaneously or one that doesn't. So if delta H was a positive, that would kind of lead towards decrease in the spontaneity. You guys ever play with the heat packs? You've got different salts that go into solution. When some of those salts go into solution, heat is released. When others go into solution, heat is absorbed. That's an interesting thing to talk about. I mean, it's a good thing to talk about at this stage. For all of those processes, when those salts go into solution, it happens spontaneously, right? Check. The ones that they make the heat packs out of. For some of them, you dump that salt into solution, and the thing cools down, right? It makes a cold pack. Others, you dump the salt in solution and it heats up. Both reactions are spontaneous. Why the difference in the temperature? Or why the difference in the heat exchange? For the ones that release heat, for the ones that you dump the salt in solution and all of a sudden a bunch of heat is dumped out, delta H is negative. That means that the electrostatic interactions of the salt in its solution are stronger than the electrostatic interactions of the salt to the solid. And so when you go from solid to solvated, there's a change in that electric potential, right? You get net movement of negative charge towards positive charge, field energy is released. That's manifested as a Q, as a heat, and so there's an observation of heat leaving the system. When the interactions of the salt the salt with the salt are stronger than the interactions of the salt with the solvent, moving from the solid to the solvated phase ends up requiring an input of energy. Normally things that require an input of energy don't happen spontaneously, but in that case, the delta S term outweighs the delta H term in the total sum of delta G. And so you'll get a reaction that happens spontaneously, even though it requires an input of heat from the environment. So it's important to remember that this entropy effect has a large, it has a lot of say in whether or not a mixing of a solution happens spontaneously. So the thing that we said about Raoult's law and the curves that we drew where there was the linear dependence on pressure and mole fraction, that approximation ends up being very good for an ideal solvent. But in the case of the solute, it doesn't work out so well. When you have pure solute, all of these guys are surrounded by other solute molecules, and so there'll be some particular pressure, and that pressure is a function of how tightly those solute molecules are held to the surface of the solution. And they're held to the surface of that solution by other solute molecules. When you dissolve that solute into the solvent, and there's just a few solute molecules per total number of molecules on that surface, on average, these solute molecules are not surrounded by other solute molecules, they're surrounded by solvent molecules. And so you can imagine that the force with which they're held into the solution is different. It might be a larger force, it might be a smaller force, whatever it is, the energy binding these guys to solution is different than in the pure. And so that approximation that we made, that P is equal to P of the pure times the mole fraction, is not so good. And so we correct for it by introducing this thing called Henry's law that I might not have entirely on this page. And what Henry's law says is that we simply take a constant, we utilize a constant that makes the relationship true. And so instead of plugging in P of the pure, we're going to put this thing in here called KH, and we're going to multiply that by XB, the mole fraction. And so essentially, we're saying that we can't say that the pressure is going to behave ideally, the pressure of the solute is going to behave ideally and be equal to P naught times XB, but we'll just make an expression that's true by fitting the observed pressure to the mole fraction by some appropriate constant. And that constant ends up being the Henry's law constant. Find the Henry's law constant by looking at a graph of pressure of the solute times the mole fraction of the solvent. And that graph will have some curvature, and mole fraction is equal to 1. This guy will be P of the pure. And if you take this curve and find a line that is tangent to it as mole fraction goes to 0, the slope of this line is equal to your Henry's law constant. And this just simply, what we're doing is we're finding a mathematical expression to fit the observed behavior. On this graph, it suggests that P here in this range varies linearly with mole fraction, and so the pressure is going to be some constant times the mole fraction, where that constant fits the slope of that curve at mole fraction is equal to 0. But you can tell already that at mole fractions that are much larger than 0, this doesn't work out so well. Because obviously the slope of this curve here is different than the slope at some other mole fraction x2. So Henry's law only works for dilute solutions, dilute ideal solutions. If we have a solute that's not obeying Raoult's law and it's obeying Henry's law instead, we can recast its chemical potential based on Henry's law. We say that the chemical potential of the species is equal to mu naught plus RT times the natural log of the observed pressure, where the observed pressure is equal to the Henry's law constant times the mole fraction. Group these two terms together into a mu that talks about the chemical potential of that thing when it's acting as a solute molecule, and we get that the mu of the solute is mu naught plus RT times the natural or log of the mole fraction. This is equation 6.16. Okay, saw that for these ideal solutions, and for most solutions that, or anything that makes a solution, that the solvation of a solute lowers the chemical potential of the solvent, right? The chemical potential of the solvent went as mu naught plus RT natural log of the mole fraction. Mole fraction, or natural log of the mole fraction, is negative, and so the chemical potential of that solute species lowers whenever we dissolve something in. So it's at a lower chemical potential energy. Remember that we've been looking at graphs where the chemical potentials, as they vary with some variable, were plotted on the same space, and we looked at the points of intersection, and we said that the points of intersection were points of equilibrium between different species, right? So let's look at a similar set of graphs, and right now what we're trying to home in on is the effect that changing the chemical potential of the solute or the solvent has on the boiling point and the freezing point. So if we have chemical potentials of the liquid phase and the solid phase plotted on the same curve, remember that the liquid phase had a larger slope because it had a larger entropy, right? If we're looking at temperature dependence, it had a larger entropy. The solid phase had a shorter slope because it had a smaller entropy. A given point of intersection where the chemical potentials were equal, this would be the fusion temperature. By dissolving a solute, we lower the chemical potential of the liquid phase. So we can drop this bar down to another point. And we look at the new point of intersection between the solid phase and the liquid phase, and we see that that point has shifted to a lower temperature. This is temperature here on that axis. What that suggests is that the freezing point has been lowered. What does that mean physically? The way that I think of this, and the way that it's been explained to me, is the following. When a liquid moves into its solid form, it has to take on a crystalline structure, right? We're familiar with this concept. When you have a solute species dissolved in a solvent, that solute species, while it is perfectly happy being here in the liquid phase, cannot fit into the crystal structure of the solid phase. And so for this guy to form a solid, a solvent to freeze to form a solid, it has to kick out all of these solute molecules. But those solute molecules are bound by interactions, electrostatic interactions. They're hanging on tight. And so it's going to take a little bit more push to drive solvent that had some dissolved solute into the solid phase than it will to convert pure solvent, right? You've got a pure solvent, you drop the temperature down, you suck out enough thermal energy from this thing, eventually all of the solvent molecules are able to align together and make whatever bonding interaction they want to make, and they solidify. Over here, it's not so easy for them to do that. Before they can solidify, they've got to break all of the interactions that are happening here with those solute species, and they have to fight against the entropy changes as well, right? And so it takes a lower temperature to get this guy to solidify when there's a dissolved solute species than it does when there isn't. And that's kind of the behavior that we're displaying here with this graph. Boiling point, same kind of thing, a little bit different explanation. So for the boiling point, we've got our intersection